All right, so our objective essentially is to use the derivatives that we've been talking about, first and second derivatives, to find information about rational functions today. This will help us with our graphing of rational functions and also any applications with rational functions. So we have learned a couple things in advanced functions which are kind of like little shortcuts that we can use to find information about like asymptotes of rational functions. That was like right toward the end of the advanced functions course. So there's a vertical asymptote at some value x equals a of a rational function, and that would be where g at a equals 0, right? So the x value that makes that g at x function, whatever it may be, equal to 0. Okay, so essentially just the 0 of the denominator is what we're saying. So as the limit approaches that particular value of our function, our rational function, we are going to get one of two things. We will get positive infinity or negative infinity, because we know that if I have kind of like a vertical asymptote, either it's coming toward my vertical asymptote and curving up, or it's coming toward my vertical asymptote and curving down. So we're kind of interested in which one of those things is happening. And what you will also notice is that when you sub in that particular value, because usually when we evaluate limits, we start by subbing in the value. You can actually know if you're approaching a vertical asymptote if you sub in right away. You'll get a number over 0. Okay? And that's how you kind of know that you're approaching a vertical asymptote. It doesn't tell you whether it's positive infinity or negative infinity. You have to do some tests to see that. Mark? So what we do when we're evaluating any limit is we usually just start by trying to sub in the value that the limit is approaching. So if I sub in a, so maybe we'll put that in. If you sub in a, you'll get number over function. Or sorry, number over 0. Okay, so in general, in plain English, we're going to get the 0 of the denominator. And there's, of course, the sign chart that we want to use to kind of figure out what's happening around there. So when we actually find this like vertical asymptote, this is going to be one of our critical numbers. So we're going to use it in the sign chart. Okay, and then I can actually tell two different things by my initial substitution into that limit function. So when I sub in a in for my rational function, whatever it may be, I might get one of two things depending on what the function is doing. Now, when we were back in grade 11, we learned about like simplifying rational expressions, and there were two results that we could get from restrictions. One of them is when my restriction, after I've fully simplified, is left in the final answer, it produces a vertical asymptote. But if my restriction gets canceled out along the way, it's not a vertical asymptote. It's actually just like an undefined point. So I can actually just do an initial test in my limit. And if I get number over function, I can assume that that value gives me a vertical asymptote. But if I get 0 over 0, that's actually just an undefined point in my graph. It's just like a hollow point. So when you sub in, or I guess we'll just say sub into the limit, and I'm going to show you an example of what I mean. Zainab. I'll show you an example, and then if you still have questions, let me know, okay? Okay, so in this guy down here, I can do a couple different things, right? So I can obviously first factor this, and that's a difference of squares on the bottom. And I think we see that when we factor this, we have restrictions where x cannot equal -2, and x can also not equal +2, right, from that denominator. And we also see another thing. We see that I can cancel, and I'm left with 1 over x squared for my function here. Or sorry, not x squared, x minus 2. So there's two different ways that we can kind of remember this. So the first way that I like to kind of teach my grade 11s, because they don't do limits or anything like that, is if this gets canceled out along the way, that -2 part that was once the restriction there, that's actually just an undefined point. It gets canceled along the way. But whatever remains in the final answer here, the restriction of that, that's going to be your asymptote. So I can see that in my final equation here, 1 over x minus 2, the restriction is 2. I'm actually going to get a vertical asymptote at that value. Now the tests that I'm talking about is when we are looking at, we don't even have to sub it into the limit. We can just sub it into the original function. But if I do a really quick test in my function of these two values before I've canceled it out or anything, let's just say we plug them right into the original function. If I sub in, if I sub in, let's start with -2. Okay, you'll notice here that I actually get 0 over 0. Okay, that should automatically tell me that I have an undefined point rather than a vertical asymptote. So that's another little test that we can do. So because we got 0 over 0, we get undefined point for that value. But if I test my other value in my original function, 2, you'll see we actually get 4 over 0. Okay, and if I get something like that, that's telling me that that restriction produces a vertical asymptote. Okay, so you can actually see the graph of the function over to the right here. So here's our vertical asymptote at x equals 2. But this function also actually has like a hollow undefined point at -2 over here. Zainab. So it's the zeros, anything that would make the denominator 0 is the restriction, right? No, because I can have 0 over 4. That's just equal to 0. But if I have 4 over 0, that's not a number. That's undefined. Olivia?
So when you mean undefined, it's always
So it's either an undefined point or it's a vertical asymptote. And I can do a quick test in my function and see if I get 0 over 0. Or a number over 0, right? If I get 0 over 0, undefined point. If I get, right, like what I drew on there. Yeah. Good. Okay, so that's vertical asymptotes and undefined points. Any questions before we move to horizontal? Okay, let's go over to horizontal. So I'm going to kind of explain this with the limit definition. It might be a little bit hard to understand until we do an actual example. So if you don't get it when I'm kind of like explaining the general notation, don't worry about it. So L is going to be some finite number. Meaning it's not like we don't get infinity, negative infinity, that type of thing when we approach the limit of the horizontal asymptote. So what we're actually looking for to find the horizontal asymptote is when x is approaching infinity and negative infinity. So we can try both of those things for our function. Oops. and we are going to get some number L. Okay, and I can't give you an exact value for this, but I can tell you just in plain English that L is the ratio of the coefficient of the highest degree of the numerator over the same highest degree of the denominator. So again, I'll explain to you when we do an actual example, but ratio of the coefficients of the x's with the highest exponents. Sorry, I should have put coefficient somewhere in there. Ratio of the x's of the coefficients of the x's. Sorry. From the highest degree of the numerator over highest degree of the denominator. Who is calling you at 9 in the morning? That's what I want to know. Oh. It was an alarm. That makes so much more sense. Have fun. Smile big. Okay. So what does this mean? Okay, firstly, we need to look at our numerator and denominator. And out of both expressions we see, we need to find the x with the highest degree out of everything. So what's the x with the highest degree in example 1? 2. So x squared has the highest degree. Good. And that's both on the top and the bottom, right? So this one's actually pretty easy because we can see both of them. The horizontal asymptote is actually just the ratio of the coefficients of those x's. 1/2. So we get the line y equals 1/2. Okay, now the second one is a little bit different. Where is the highest degree that you see out of the numerator and the denominator? Zainab? X cubed. Okay, so what we might do is just kind of rewrite this so that we actually have an x cubed on the top. But our x cubed on the top is going to be 0x cubed because we don't see it. But we need those degrees to match. So if that degree is not there, then it's 0x cubed or whatever the highest part is. Okay, and then once we have that, the ratio of those x's with the highest degree, whoops, please hold, is 0/6. So this is okay, right? I just can't have like 6/0. So my horizontal asymptote is actually at the value y equals 0 here. Okay? Mark?
When the denominator has a higher degree than the numerator, we sub it.
Yep. Okay? Any questions? Gabriella?
If it's like a way like the highest degree at the bottom is like 6x and 5, and then you have the same thing, you just
Yep.
plug in the 0.
Yep.
Do they have
Yeah.
to be the same degree?
Yep. So we're just going to make it the same degree, whether or not we see that like highest degree there. We'll just say it's 0 if we don't see that particular degree, whether it's like 6 or 10 or whatever. Gabriella?
And then if it was a number over 0, then it would be
So actually that brings us to our next point here. So the horizontal asymptote only exists if your degree of your numerator is less than or equal to the degree of the denominator. So I cannot, if I'm trying to find horizontal asymptote, I cannot have a horizontal asymptote for a function that is like the reverse of this, let's say. If this were reversed up here, this example, I actually have what's called an oblique asymptote, and it's like a diagonal asymptote. So we don't have a horizontal asymptote for those guys. Okay? So either they're equal or the degree is higher, or degree of denominator is higher. Okay? Cool. All right, so we're going to kind of do some similar things as what we did with polynomials, except in order to find how the graph is reacting at these vertical asymptotes, we're going to kind of do some tests, and then eventually we'll use derivatives to help us as well. So for this one, we're actually just only going to use the original function, and we're going to test the limits from each side as we approach those vertical asymptotes. So can somebody tell me what my vertical asymptotes are? -2 and +3, good. So vertical asymptotes are found where x equals -2 and along the line x equals 3. Now what I want to do to just test these in the original function is I'm going to test some of the limits as we approach from the left and the right of each of these things. So I'm going to do 4 tests because I have 2 asymptotes, 1 from each side. Okay, so let's start with -2. I want to test the limit as we approach -2 from the left for our function f of x. Okay, this can be maybe a little bit hard to do because we can't just like sub in, right? Because it's just going to give us vertical asymptote. So what we have to do for these tests is we need to test a value that is, like if we think about a number line, and -2 is here, maybe -3 is over here. I want to test as we're coming from the left toward -2. So maybe something I might test is like -2.0001. And all I'm really concerned about, I already know that my graph is either approaching positive infinity or negative infinity. So all I'm really concerned about with my test value is whether I get negative or positive, and then I'll decide positive infinity or negative infinity based on that answer. Gabriella? So this means from the left.
And then there was nothing there that would be from the right?
No, plus is from the right. Okay, so maybe we test something like this, okay? Lauren?
So if you're doing -2 from the left, you go past -2, like it wouldn't be 1.999.
So that's from the right. Yep. Okay, so we're approaching -2 from the left, so I'm going to sub these guys right into my function. And again, all I'm concerned about is really negative or positive, because from that I can make a decision on positive or negative infinity. Mark?
Why did you put -3, -1 or does that not matter?
Why did I say that one more time?
Why'd you put -3, or positive? Yeah, -1 and -3, like on the side. Like why was that where you decided?
Because that's what goes in a number line, that's what surrounds -2. Does that make sense?
Does it matter?
No, it matters. I want things on both sides of -2. I'm just showing you on a number line, just a regular number line, what's going on. Does that make sense? Okay. Sorry, I'm trying to get this to erase and I'm having trouble. What did you guys get? Sorry, what? Okay, but what number do we get from this?
199. I might have done. I did 0.001. Oh yeah.
So did I.
199.96.
199.96. Okay, that's fine. I could have even, if I wanted to, I could have subbed in -2.5. All I'm again concerned about is whether that's positive or negative. Zainab?
So the negative and positive, what does that have to do with
So whenever we're approaching vertical asymptotes with rational functions, if we look back up at our kind of explanation here, I'm either approaching positive infinity or negative infinity. I'm just trying to figure out which one it is from each side. Okay? You'll see when we do the sketch too. This one does have more than one asymptote, so I'll show you. We're going to test from each side for both of them. Okay? Okay, so this guy is positive infinity. Sorry, I tried to erase that line, but it won't let me, so it's going to stay there. Yep, it's just going to stay. How do we know it's positive infinity again? Because the number was positive in our test. Okay, good. Now I want to test the limit as x approaches -2 from the right of our function f at x. So a test that we can do, maybe I choose something on this side. So as I come from the right, I'm coming from -1 toward -2. So I want to choose something like maybe -1.99. Maybe we choose -1.999. Doesn't matter. Gabriella?
So for all those values that you test, like, it can come from the left and the right?
Yes, we want to test both sides because it might be doing different things on either side of the asymptote. So I want to see what's going on both sides. Yep.
So because it's positive for -2, it's going up.
Yeah, so it's going up as it goes toward that asymptote from the left. We're going to do a little sketch, so if you guys are like confused about what it is that we're finding right now, you'll see once we graph it. Okay, so what do we get for this guy? Did you do? Okay.
That's for, yeah, like 3 nines.
Okay, perfect. So somewhere around -200, this tells me that the limit is -infinity. Okay, so here's what I know. As we're going toward the -2, as I come from the left, we're going up toward positive infinity, but then as I come toward the right, we're curving down toward -infinity. Okay, now I want to do 2 more tests. We're going to do tests for 3 from the left and from the right. So the limit as x approaches 3 from the left of our function. Okay, guys, let's focus in here. Shh. Sorry about the line. Okay, so what might I test in this function if I'm approaching 3 from the left? Sure, or even just like 2.9 you could do. So let's say we choose 2.99. Again, I'm doing that because when I have the value 3, I have 2 and I have 4. And if I'm coming from the left, I'm coming from 2 toward 3. I'm approaching 3 from the left. So that's why we're choosing something like 2.999. Okay, so we're going to sub that into our function. I don't think I need to show you the substitution every time. We're just doing the same thing. Lauren?
Why for this one is even 2.99, but the other one you went over it's like 2.001?
So again, you just have to use your common sense here. Like, we're approaching from the left, so I need something that's on the left side of 3, like coming toward 3, right? Yeah, positive, yeah. So that makes a difference too, right, when it's positive and negative. Okay, so did anybody do 2.999? -20?
200.
Oh, I think we got -200. Okay, so -infinity for that guy. And then last one, limit as x approaches 3 from the right. Maybe we choose something like 3.001, something like that. Oh, sorry. Did you calculate this one already too?
Yeah, 199.96.
Perfect. So we can assume this one's going up toward positive infinity then. Okay. So where is my horizontal asymptote for this function? Where is the horizontal asymptote? Well, let's look at the degrees up here. What's the degree of the denominator? 2, right? Because when I expand this, I get this, right? So what's the horizontal asymptote?
Does
not one.
exist.
Nope.
D and 0
So my x squared degree up here, it's like 0x squared plus 1, right? Over x squared minus x minus 6. So what's the ratio of these coefficients? 0 over 1, right? So my horizontal asymptote here is just y equals 0. Okay, this is very similar to what we just did right here, right? When I don't have that degree, it's going to be 0. Right? Okay, so horizontal asymptote at y equals 0. Lovely. Okay, so we're going to start by plotting our asymptotes. We did both of them, from the right and the left. Sorry, I'm just going to restart this quickly, guys, because my eraser's not working. Okay, guys, we're going to take a little break right after this, but I need you to be quiet for right now. Silence. Okay, so draw your asymptotes where they should be. See if this erases now. Yes, good, okay. Okay, so there's a couple things that we know. We know as we approach 3 from the right, we found that we are approaching positive infinity. I also know that my graph can't really cross through that horizontal asymptote, so I know that we're not approaching infinity from down here. That doesn't make sense, because then I'd go through my horizontal asymptote. So my common sense tells me that that section of the graph is probably doing something like this, right? And going, oh, sorry, that was an accident. Doing something like this and going up toward positive infinity, because it can't go through that horizontal asymptote. So if it's going up toward positive infinity, it must be above the horizontal asymptote. Okay? Now if we look at 3 from the left, it's actually going down toward negative infinity, so maybe something like this. And then this one's interesting because we have kind of like an asymptote bordering 2 sides of this section. So I actually want to look at what's happening as we go toward 2 from the right now. So as I go toward the asymptote negative 2 from the right, we can see that we were going down toward negative infinity. So I've probably got something like this happening. Yep.
Why do we have to test if we know that the denominator, like we already know the vertical asymptote?
Yeah, but we're seeing where the function is curving around, like whether the function is curving up or down at those areas. Yeah. Okay, and then what were we approaching as we approach negative 2 from the left? So as we come from the left, we're approaching positive infinity. So that tells me that we've probably got a section of the graph going like this. Okay, again, I know what sides those are on because I can't go through the horizontal asymptote. So if I tried to do this where my graph was up here, okay, well, I'm going through the horizontal asymptote there. So I just need to be mindful about not doing that. That's how we know where to place those. Gabriella?
And you got the horizontal asymptote and then the 0 over 1.
Yeah.
And that's equals 0.
Yeah, exactly. Zainab, did you have a question? Yep.
That's just the same for if it's coming from 2 different rows, right?
So imagine I'm starting here. If I'm going toward 3, this is from the left. But if I'm going toward negative 2, this is from the right toward the left, right?
Yeah.
So that's what I'm looking at. Any other questions for this one? Okay, let's take a couple minute break here, and then we'll resume. All right, so we are going to use our derivatives now on our rational function, knowing what we know about how to find asymptotes and things like that, as well to help us develop our graph. So firstly, before we even start anything here, or actually I guess it's part C, but I'm going to do part C first. Because I want to know, just by looking at the original function, what's the information that we can tell about this graph? Well, firstly, we should be able to identify if we have any vertical or horizontal asymptotes. So do we have any values that could make the denominator 0 here? So if I sub in -1 there, I square it, and then I get +1 plus 1, which doesn't give me 0. Same thing. Okay, so no vertical asymptote, agreed? What about horizontal asymptote? Okay, good. So our horizontal asymptote, so again, we want to kind of think about this as like 0x squared, right? When we're thinking about our horizontal asymptote, so it's like 0 over 1. So here our horizontal asymptote is again y equals 0. Yep.
But like, why wouldn't it be like, oh, because the square root of, like when you're solving, like when you set the bottom to 0.
Then I'll have to square root a negative, right?
Okay.
I'll get this, and then I would have to square root a negative, which we know we can't do. Yep. Okay, good. So C is done. Now to find the intervals of increase and decrease, what am I going to use? First derivative in a chart. Okay, good. So we want to find the first derivative, which means when I'm working with a rational function, I have to do quotient rule. Okay? So one thing that we do want to remember is that the order of quotient rule is actually important here. When we do product rule, it doesn't matter the order because we're adding, but when I do quotient rule, the order does matter because we're subtracting on top.
Can you
Yeah.
just bring the denominator up and it becomes x to the -2 plus 1?
You could do this if you wanted and use chain rule,
Okay.
but not that single term
Okay.
because it's being added with a 1.
Can you bring the 1 up too? Because wouldn't the 1 just become 1 and the -1?
No, you can't do that with like individual terms like that, only if
Okay.
they're being
Oh, you have to bring
multiplied.
the whole thing, okay.
Yeah. Okay, so derivative of the top, which is 0, times the bottom, minus the top, times the derivative of the bottom, all over the bottom squared.
Wait, which one's first? Is it, so it's the,
Top prime times the bottom, minus the top times the bottom prime. Good? Over bottom squared. Ryan? Yeah, this is quotient rule. Okay, so this whole term on the left here, that's just gone, right? Because it's being multiplied by 0. So I'm actually just left with -2x over x squared plus 1, all squared. Okay, critical numbers here. So the critical numbers are, again, anywhere that our first derivative is equal to 0. Where is my first derivative going to be equal to 0? Maiwa? 1 and 2? Oh, when the numerator is 0. Okay, so when is the numerator 0? When x equals 0. Okay, so my critical number is when x equals 0. That's the only time that whole expression right there is going to equal 0, right? Because if I sub in 0 for x, I'm getting -2 times 0 over 1 squared. And then I get 0 over 1, which is 0. No, our horizontal asymptote, this is different. This is a critical number. Okay, so in order to find the y-coordinate of this critical number, I evaluate f at 0. And I get 1 over 1, which gives me 1. So far, so good? Okay. All right. So we're going to make a chart. We only have one critical number, so we only need one line in the middle there. Choose some test values. And remember, we test these in the first derivative. We're not testing them in the original function. So I'm actually plugging them into our function here. And I just want to record whether we get positive or negative. And actually, because the bottom is all squared, I'm only really interested, like I could just look at the top, because the bottom's going to be positive always because I'm squaring it, right? So if I look at plugging in -1 to this top part, I get positive. But if I plug in 1 there, I get negative. So that tells me increasing and decreasing. Gabriella? I'm plugging it in here to the first derivative in for the x's. Sorry, I actually can't hear you very well because there's so many people talking. What did you say, the second part? -1. So I have to test in this interval, right? So I'm just choosing values in those intervals. Okay, so here is an interval of increase right here. So if I'm telling the interval of increase, it's from -∞ to 0. And this guy is an interval of decrease right here. Mark?
Did you plug in 0 to f of x? Is that what you-
Yes, so that I could find the critical point at 0, 1. Okay, so that's A done. And then we're going to find the point of inflection. It actually doesn't ask me to find areas of concavity here, but we're going to do that because we're sketching a graph. So we're going to find intervals of concavity as well. Okay, so part B, second derivative. I am taking my first derivative. Yep, Zainab. Point of inflection, yeah, when the second derivative is 0. We haven't done it, no. Okay, so derivative of the top, is that -2? Yeah. Times the bottom, minus the top, times the derivative of the bottom. Okay, this is going to be a chain rule kind of thing. So we're going to get 2. And then subtract 1, so that leaves us with an exponent of 1, times the derivative of the inside, which is 2x, all over the bottom squared. So when I square a squared, I get exponent of 4. So usually what I like to do before I start expanding and simplifying is actually just like look on the top and see if there's any common things that I can maybe common factor out to make my life easier. So do you guys see any common things on the top that we can maybe take out? There's a -2, potentially, that we can take out. There's also x squared plus 1s, so I can take out one of those. So maybe we take out a -2 x squared plus 1, and then we write what's left. So I'm going to have 1 x squared plus 1 left here. And then my -2 here is gone, so I've just got x times 2 times 2x. You can simplify that all if you want. Oh yeah, that makes sense. Okay, so just common factoring. And then I can actually reduce out front here. So I'm going to take out one of these with one of these on the bottom. So I'll just have 3 of them left on the bottom. Okay, and we're just going to, in order to see what the 0 is of that numerator, I'm just going to simplify in here. So it looks like this is just 4x squared. So I have x squared minus 4x squared. That gives me negative 3x squared plus 1. And I'm interested in where this is equal to 0. I actually don't know if I set the first derivative equal to 0, but. Mark, question. Oh, my eraser's not working again. This? This? Yep.
When you factored out the negative 2x squared plus 1,
Yep.
why didn't it change like the sign of 2?
The sign of what, 2? There's lots of 2s.
First 2, like before the x squared plus 1.
So I took that out though, right? So the only thing that I'm left with in this term right here is 1x squared plus 1, which is here. So the green part is the common factor that I took out. So the question is, this expression right here is going to equal 0 where the numerator equals 0. So my question is, where is the numerator equal to 0? Well, I can actually really just set, no, it's not 0. I can set this equal to 0 and just solve for the value that makes that true. I'll take that out. Sorry. And then we can actually just positive and negative square root this guy. And when I square root 1, I just get 1. So it's really just like positive, negative square root of 1 over 3 equaling square root of each of those, numerator and denominator. Okay, so I can actually, when I'm dividing underneath a root, I can take the roots of each of those individual things. As long as there's no like, yeah, that's fine. These are my points of inflection, or the x-coordinates of them at least. So far, so good? Okay. All right, let's do our sign chart quickly here. I don't have tons of room left, but I'll do it over to the left here. Okay, and it might be helpful for us to know that 1 divided by root 3 is approximately equal to 0.57. So when we choose our test values, I'm choosing something between negative infinity and negative 0.57. So maybe we choose like negative 2, for instance. And then we can choose 0 here. And then maybe over here we choose positive 2. Okay, and we want to sub these into the second derivative. So I'm going to sub them into my simplified second derivative. And again, because I'm squaring this right here, the bottom of that fraction is always going to be positive anyways. So really, I'm kind of just interested in the top of this, although you can sub it into the whole thing if you really want. So negative 2, I think we're getting positive there. Correct me if I'm wrong for any of these, please. And then negative, and then positive. So we're concave up in 2 intervals. and then concave down on the one interval there.
Is the sign chart necessary to find the point of inflection because it, like one point, like the test might fail at one point? Is that why? Like if you got 0.
Are they necessary to find points of inflection? No. They're just, I added, we're going to find intervals of concavity to that second part.
Okay.
Yeah. Okay, the other thing that we were actually asked to do is find the actual point of inflection. So I'm just going to take one more second, we're almost there, to evaluate f at 1 over root 3 and f at negative 1 over root 3 so that I can get the y coordinates of those points of inflection. Okay, so subbing into this original function here. Okay, maybe somebody with a calculator that leaves things in fractions for us can find it quickly for us. Actually, I have one of those. I got 3 over 4. It'll be the same for each of them. Okay, that kind of tells us approximately where the y values are for those specific points. So that's why that's important. Okay, I think we can get a really, really good sketch here. So we've got a horizontal asymptote. I'm going to start with that at y equals 0. We have no vertical asymptotes. I have a critical number at x equals 0, and we found the y coordinate of that to be 1, which is actually kind of off our graph, but we can just add it up here. So I'll just add it to the top. It was 1, right? Yeah, 1. 0, 1, which is here. Points of inflection at like negative 5.7. That's great. And positive 5.7. And 0.75. So here-ish and here. And then we know in this little section right here, the graph is actually concave down, like so. And then in these other sections past here, our graph is concave up. So that actually probably tells me that we are kind of like curving like this around our graph toward our horizontal asymptote there. Gabriella. Yep. 3 over 4, like 0.75. Yep, because I have negative 1 over root 3 and positive 1 over root 3. That's like negative 0.57 and positive 0.57. And then the 3 over 4 is how high it goes. It's the y coordinate. So these are the points that I'm graphing here. Yeah? Okay, we have, yeah, we're going to finish the last one here. Okay, intervals of concavity. So we're going to practice our quotient rule again. Let's start by finding f prime. We're going to do this quickly. 0, derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. And we're just going to simplify this just for the sake of finding the second derivative a little bit more easily. Okay, second derivative, I'm not interested in the first derivative. This is just asking me about intervals of concavity. Second derivative, so again, derivative of the top times the bottom minus the top times the derivative of the bottom. And when I do the derivative of the inside, like when I'm doing chain rule, I just get 1 for that over the bottom squared. So when we simplify, oh, sorry, this is 2, not 1. X plus 2. So when we simplify here, we can actually cancel out one of those x plus 2's. Yep. Okay, so I would expect that these kinds of derivatives are relatively quick at this point, okay? So if it takes you longer than it takes me, that's totally fine. But we should be able to find those derivatives, and we should be able to do them correctly, right? Okay, so here's a problem. I want to know where this equation is equal to 0 so that I can find like a point of inflection here. Is this function ever going to equal 0? At -2, I get undefined, right? So the second derivative is actually equal to 0 nowhere, okay? This has no solution. So one kind of important thing here is that we actually include any vertical asymptotes in our chart for our second derivative. Now, our example before didn't have any vertical asymptotes, which is why we didn't have to worry about that. But this one in particular is interesting because it has no point of inflection, but there may still be an area where we change concavity, and that could be on either side of the vertical asymptote. Okay, so what we need to do is we want to create a point of, not a point of inflection, but we still want to create our chart that tests, but we're going to use the vertical asymptote as our kind of important point that separates those areas. Okay, so we're going to create a table to test the second derivative. Mark, question?
So like with the graph, just for like straight lines, right?
No, so it doesn't mean that we don't have any concavity. It just means that there's no point of inflection. But even if we don't have a point of inflection, it could still change concavity on either side of an asymptote. Okay, so we're going to create a table to test f prime of x, and we're going to include the vertical asymptote. What is the vertical asymptote? -2. Good. So we must include our vertical asymptotes in our table.
I think can you explain why -2 over x plus 2 cubed has no solution?
Well, the only thing that I could potentially plug in here to possibly get a 0 is -2, but that doesn't give me 0. It gives me number over 0, which is undefined. That's why.
No matter what, I feel that's how
Pardon?
yeah.
Yeah? Okay. Okay, so we're testing these in our second derivative. To check out concavity, and we have a vertical asymptote here, so it's actually not a point. Do we have a horizontal asymptote?
Yes. Y equals 0.
Yeah, it's y equals 0, right? Okay, so this is concave up. Guys, we're almost done. Focus in here for the last couple seconds. It's concave up from -infinity to -2, and concave down from -2 to infinity. Okay, so what does this tell us? Well, let's just sketch what we can to start, and then we'll kind of make some decisions from there. So I've got this vertical asymptote. I've got the horizontal asymptote. Okay, I know that my graph is concave up from -infinity to -2. Okay, well, I could have concave up down here somehow, but we can actually see that that's going through all of my asymptotes, so that's probably not happening. So I probably have concave up and above the x-axis, and it's probably just wrapping around those two asymptotes like so. Okay, and then if I have concave down, of course it can't really be over here, because again, I'm going through my asymptotes if I do that. So I don't want to do that. So it's probably concave down and below the x-axis, kind of like so. Okay, these functions should be relatively familiar to you from advanced functions, right? We did number over function in advanced functions. So we are simply using derivatives to find information about these functions, but we should already know how to graph these functions from advanced functions. We did those.